This is my Capstone lab for Physics 1. The purpose of this lab is to model a perfectly inelastic collision in order to investigate how momentum is conserved when two objects collide and stick together. By measuring the masses and velocities before and after the collision, I aim to compare the system's initial and final momentum and evaluate how closely the experimental results match theoretical predictions. So what are the physics that are in the background here? Well, there's two main types of collisions that we cover in physics. The first is an elastic collision, and the second is an inelastic collision. In an elastic collision, the objects collide and then they move separately after the collision. In an inelastic collision, specifically a perfectly inelastic collision, the objects that collide then move together after the collision as they stick together. In an inelastic collision, we define it as kinetic energy is not conserved, whereas an elastic collision we define in which kinetic energy is conserved. But for both types of collisions, total momentum and total energy of the system are conserved. Specifically in this lab, we are going to study a perfectly inelastic collision. Before the collision, the objects move separately with their own velocities. However, after the collision, the objects stick together and move together with one velocity. How do you solve these collision problems? We're going to take a four-step approach. We're going to first calculate all the known momentum for the objects before the collision. Then we're going to calculate all the known momentum for the objects after the collision. Then we're going to equate the total momentum before the collision to the total momentum after the collision. And then we're going to solve for whatever we have as an unknown. The main takeaway of this lab is that the experiment showed that even when two objects stick together in a collision, their total momentum stays nearly the same. It's just redistributed between them after they combine. Key assumptions that I had to make in this lab are as I was assuming one-dimensional motion only. I'm only looking at motion in the x direction. I'm also assuming all forces that are external or in the surroundings to be negligible. In other words, we're going to say that this track that the two carts are moving on is frictionless. We're also going to assume that the carts themselves are of equal mass with each other. And then we're also going to assume that accurate scaling and a measurement was achieved through the calibration stick in tracker. This shows our experiment that we did. In this experiment, there was two carts that each had mass. The cart on the left had a mass that contained an extra mass of 0.500 kilograms on it. And then the surroundings are everything outside of the colliding masses. For our experimental observations, we show mass A and mass B. Mass A was the cart that was slightly heavier, and mass B was the cart only that didn't have the extra mass on it. If we can see, when they collide, then they move with the same velocity after they collide together and stick together. In terms of our experimental data, I found the average velocity for both mass A and mass B, and I used their masses, and I multiplied those two together to find the initial momentum of each cart, and then I added those to find the total momentum initially of the system. Then I found the final combined velocity and used the same and multiplied it by the combined masses to find the final total momentum of the system. If we can see, conservation of momentum was not achieved. Then I decided to code this and use GlowScript to find the theoretical results. This code that I created models two different masses that are colliding with the same initial speeds. I initialized one mass to be 0.5 and the other mass to be 0.1, so they differed like in my real experiment. Both were moving at the same velocity, just in opposite directions toward each other. This is what my computational model looked like. If we can see, both the initial momentum and the final momentum were the same and equal. That means momentum was conserved. However, the initial kinetic energy and the final kinetic energy were different, showing that this was an inelastic collision. In my actual experiments, potential sources of error include model assumptions, such as I assume the two carts to be of equal mass. However, I'm not entirely sure if this was true. Additionally, I assumed all external forces in the surroundings to be negligible, such as mainly that the track was frictionless. However, there was likely friction on our track. In terms of our final conclusions for this lab, the first question that I created is, what if friction on the track increased? If friction was increased, momentum would appear to not be as conserved. Friction represents an external force acting on the system, and this external force would slow both carts down more before and after the collision, so the final momentum in the real experiment would likely be less than the initial momentum. However, if we had included the friction, in our system, momentum would appear to be conserved still. This just matters on your choice of system. What does it mean if the combined mass moves slower after the collision? Well, conservation of momentum means that the total initial momentum should equal the total final momentum. This means that after the two objects stick together, the same momentum that was spread between the two objects is now shared between one larger combined mass. We also know that momentum equals mass times velocity. Thus, in order to conserve momentum, if the mass increases, the velocity must decrease. This is why a slower speed is observed for the combined mass after the collision. Thank you for listening to my final lab in Physics 1.